Now let's see how to design an API. So to design an API, we need to follow some order. Like we need to first create the resources, then methods like get, post, put, patch. Then what are the requests? Request is when we use methods like post. Then responses. So these things should come in order. So let's see this by taking an example. Then finally we will see how to search data.
Now let's discuss designing APIs. So we need to understand a concept called data organization. So for example, you have millions, billions of photos. And with so many photos, you can imagine the different approaches people have to organizing them on their computers. Some people prefer to dump everything into a single folder. Others meticulously arrange their pictures into a hierarchy of folders by year, month, and event. Companies give similar thought to organization when building their APIs. The purpose of an API is to make it easy for computers to work with the company's data. With ease of use in mind, one company may decide to have a single URL for all the data and make it searchable. So with ease of use in mind, one company may decide to have a single URL for all the data and make it searchable. Another may decide to give each piece of data its own URL, organized in a hierarchy. Each company chooses the best way to structure its API for its particular situation, guided by existing industry best practices. So when we design APIs, so we need to start with few things in order. We need to design the resources first. Then we need to give the methods. Then we need to send the request if it's there. The next is we need to get the response. So these things should go in order. So when we design APIs, we are just creating the behavior of how it behaves. The response, what you get, will be a sample response. Then when you connect the APIs with the system, you will get the actual responses. So we need to start with an architectural style. When designing APIs, you might hear talk of SOAP and REST and wonder whether the software developers are doing work or planning a vacation. The truth is that these are the names of the two most common architectures for web-based APIs. SOAP is an XML-based design that has standardized structures for requests and responses. REST, which stands for Representational State Transfer, is a more open approach, providing lots of conventions, but leaving many decisions to the person designing the API. So we might have included an inclination for REST APIs. The preference is largely due to REST's incredible rate of adoption. This is not to say that SOAP is not good. It has its own strong points. However, the focus while designing the APIs will stay on REST, as this will likely be the kind of API you encounter. So how to design our first resource? So resources, you can call them as the endpoints. So after the base URL, you will have several resources which are used to send the requests to that particular endpoint. Resources are the nouns of APIs. These are the things we want the world to be able to interact with through our APIs. To get a feel for how a company would design an API, let's try at it with our ice cream parlor example. We will start by adding the ability to order an ice cream. For the client to be able to talk ice creams with us, we need several things. So we need to decide what resources need to be available, assign URLs to those resources, decide what actions the client should be allowed to perform on those resources, and finally figure out what piece of data are required for each action and what format they should be in. So picking up the resources can be a difficult task at first. One way to approach the problem is to step through what a typical interaction involves. For the ice cream example, we probably have a menu. On that menu are ice creams. When a customer wants us to make one of the ice creams for them, they place an order. In this context, that is the ice cream from the menu. Customer and order all sound like good candidates for resources. So for this example, we can have the resources like menu, ice cream, customer, and order. So first, let's start with the order. So picking resources can be a difficult task. One way to approach the problem is to step through what a typical interaction involves. For our pizza parlor or for our ice cream order, we probably have a menu. On that menu are ice creams. When a customer wants us to make one of the ice creams for them, they place an order. In this context, the menu, ice cream, customer, and order all sound like good candidates for resources. So first, we will start with the order. So the next step is assigning URLs to the resources. There are lots of possibilities, but luckily, REST conventions give some guidance. In a typical REST API, A resource will have two URL patterns assigned to it. The first is the plural of the resource name, like orders. The second is the plural of the resource name plus a unique identifier to specify a single resource, like orders/order ID, where order ID is the unique number for an order. These two URL patterns make up the first endpoint that our API will support. These are called endpoints simply because they go at the end of the URL, like http anything.com/endpoint. So, as we have discussed, the first is to decide what resources need to be available. So, to do this, we can step through what typical interaction involves. For the ice cream order, we have a menu. Of ice creams. So for the ice cream example, the menu, ice cream, customer, order, all are resources. Next is to assign the URLs. So we can take some guidance from the REST architecture. So a resource will have two URLs. The first is the plural of the resource name, like orders. And the second is the plural of the resource name plus a unique identifier to specify a single resource, like /orders/order ID. This order ID is a unique name, unique number for an order. These two URLs make up the first endpoint that our API will support. So they are called endpoints because they simply go at the end of the URL. So if the base URL is http:// anything.com, then the endpoints will be after this base URL. So for our example, we have two endpoints. One is the orders and one is the order ID. Now that we picked our resource and assigned it URLs, we need to decide what actions the client can perform. Following REST conventions, we say that the plural endpoint, that is the orders, is for listing existing orders and creating new ones. The plural with a unique identifier endpoint, that is order ID, is for retrieving, updating, or cancelling a specific order. The client tells the server which action to perform by passing the appropriate HTTP verb in the request. So altogether, our API now looks like the format like this. So we can summarize the methods that we will use in our API. That is, HTTP methods can be get method, post method, put method, delete method, patch method, or we can just stick to these four methods. And the endpoint, if we write /orders, get /orders, post /orders, then get /orders/to. Get orders/for. Put orders/1. Delete orders/1. So you can very well guess the meanings of this. Made. So it will fetch the existing orders, post, place a new order, get order, get details for order #1, get details for order #2, or these numbers, updates order with ID 1, or you can say delete the order with ID 1. Now, with the actions for our order endpoints fleshed out, the final step is to decide what data needs to be exchanged between the client and the server. So we can very well place this for the third step. Borrowing from our ice cream order example, we can say that an order needs flavor and toppings. We also need to select a data format that the client and server can use. So borrowing from our ice cream order example, we can say that an order needs flavor and toppings. We also need to select a data format that the client and server can use to pass this information back and forth. XML and JSON are both good choices, but for readability, let's take JSON. So at this point, you should look at the format. We have designed a functional API. So the interaction between the client and server may look like this using this API. So the client sends the post request for orders with the name and the toppings. So this, he sends it to the server. Then the server sends back a response to the client that the order is placed successfully and the status code is 201. So for this, the ID will be 4. Now later, the user wants to update the order by changing the toppings. So then it looks like this. Or we can change the name to Mango. Then finally, the client also sends a response to the server sends a response to the client that the update is successful. Now that we have created some resources. Now, how to link resources together? So let's imagine that we decide to start tracking orders by customers. So to do this, we have to add a new customer resource. So just like with orders, our customer resource needs some endpoints. So just like with orders, our customer resource needs some endpoints. So according to the conventions, we will go with customers and customers ID. So which will be appropriate for our example. So if we decide which actions make sense for each endpoint and what data represents a customer, assuming we do all of that, we come to an interesting question: how do we associate orders with customers? So the REST architecture practitioners are split on how to solve the problem of associating the resources. Some say that the hierarchy should continue to grow, giving endpoints like customers slash an ID slash orders for all of customers following the ID orders, and customers ID and orders ID. So others argue to keep things flat by including associated details in the data for a resource. Under this paradigm, creating an order requires a customer ID field to be sent with the order details. Both solutions are used by REST APIs in the wild, so it is worth knowing about each. So for the post method, we write slash customer slash post slash order slash 3. name vanilla, topping nuts. So this versus post order /3. Where name is vanilla, topping is 3, topping is nuts. And for the customer ID, is 3. So the customer ID is 4. And get /customers /4. Name Brian. Then how to search the data. As data in a system grows, endpoints that list all records become impractical. Imagine if our pizza or ice cream parlor had 3 million completed orders and you wanted to find out how many had a particular, for example, nuts as a topping. Sending a GET request to orders and receiving all 3 million orders would not be very helpful. But REST has a number of ways for searching through the data. So here we come across a very important parameter called query parameters. So query parameters, they begin with a question mark. When you want to search for particular records. So instead of giving /orders and getting all 3 million records, it is wise to pass a query parameter along with the orders and filter the results so that you get appropriate records. So URLs have another component known as query parameters, which means search, and parameter means text. The query parameter is a bit of text that goes into the URL at the end of the URL to pass the things along to the API. For example, everything after the question mark is the query parameter. So the query parameter goes like this. REST APIs use the query parameter to define details of a search. These details are called query parameters. The API dictates what parameters it will accept, and the exact names of those parameters need to be used for them to affect the search. Our ice cream order API could allow the client to search for orders by topping, by using the URL http://orders topping equals nuts. The client can include multiple parameters by listing one after another, separating them by an ampersand symbol. For example, if you want to include multiple query parameters, then it goes like this. The toppings equals nutses, the first query parameter. Then we need to separate it with ampersand and write another query parameter. For example, name. Another use of the query parameter is to limit the amount of data returned in each request. Often, APIs will split results into sets. For example, 100 or 500 records, and return one set at a time. This process of splitting the data is known as pagination. To allow client to page through all the data, the APIs will support query parameters that allow the client to specify which page of the data it wants. In our example, we can support paging by allowing the client to specify two parameters, page and size. If the client makes a request like get orders, page equals 20 and size equals 500, We know they want the 20th page of results with 500 results per page. So order, having some numbers, having the particular numbers come into the page. So we need to remember some keywords. SOAP, pagination, query parameters, REST, resource, endpoint. So SOAP is an API architecture known for standardized message formats. Pagination is the process of splitting up results into manageable chunks. Query parameters are the parameters sent along with the resource in the form of a key value pair to filter the results. REST is also an API architecture that centers around manipulating resources. And resource is a term for a business noun like customers or orders. Endpoint usually is a resource, but it's a URL that makes a part of an API. So each resource gets its own endpoints. Next, let's discuss about integrations. To set the stage for our discussion, let's remind ourselves why APIs are useful. So APIs make it easy to share data between two systems, be it websites, desktops, or smartphones. Straightforward sharing allows to link systems together to form an integration. People like integrations because they make life easier. With an integration, you can do something in one system and the others will automatically update. For our purpose, we will split integrations into two broad categories. The first we call client-driven, where a person interacts with client and wants the server's data to update. The other we call server-driven, where a person does something on the server and needs the client to be aware of the change. The reason for dividing integrations in this manner comes down to one simple fact. The client is the only one who can initiate communication. Remember, the client makes requests and the server will respond. The result of this limitation is that changes are easy to send from client to the server, but hard to do in the reverse direction. So first we will discuss about client-driven integration. So to demonstrate why client-driven integrations are easy, let's think the ice cream example and its API for ordering the ice creams. Just imagine we release a smartphone application that uses the API, and in this scenario, the ice cream parlor API is the server and the smartphone application is the client. A customer uses the application to choose an ice cream and then hits a button to place the order. As soon as the button is pressed, the application knows it needs to make a request to the pizza parlor API. So more generally speaking, when a person interacts with the client knows exactly when data changes. So it can call the API immediately to let the server know there is no delay and the process is efficient because only one request is made for each action taken by a person. Then we have server-driven integration. Once the ice cream order is placed, the customer may want to know when the pizza is ready. How do we use the API to provide them with updates? Well, that's a bit hard. The customer has nothing to do with making the ice cream. They are waiting on the pizza or ice cream parlor to prepare the ice cream and update the order status. In other words, the data is changing on the server and the client needs to know about it. Yet, if server cannot make requests, we appear to be stuck. Solving this type of problem is where we utilize the second category of integrations. There are a number of solutions software developers use to get around the client-only requests limitations. For example, polling. When the client is the only one who can make requests, the simple solution to keep it up to date with the server is for the client to simply ask the server for updates. This can be accomplished by repeatedly requesting the same resource, which is known as polling. With our ice cream order, polling for the status of an order might look like this. The client sends a GET request for orders/5 to the server, and the server responds back with the status ordered. Then again, if the client does a polling for the server for this get/orders/5 to the server responds back the status delivered. Right. This is known as polling. In this approach, the more frequently the client makes requests, the closer the client gets to real-time communication. If the client polls every hour, at worst, there could be a 1 hour delay between a change happening on the server and the client becoming aware of it. Poll every minute instead, and the client and server effectively stay in sync. Next, we will talk about implementation. So after understanding few stuff about APIs at an introductory level, how can we put it together for a good purpose? So let's see how to turn the knowledge into working software. So as we have seen throughout this course, an API interaction involves two sides. When we are talking at the code level, what we are really saying is that we need two programs that implement the API. A program implements an API when it follows the API's rules. In our ice cream order example, a client that can make requests to the /orders endpoint using the correct headers and data format would be a client that implements the ice cream orders API. The server program is the responsibility of the company publishing the API. In our early discussions, we looked at the process behind designing the API. After planning, the next step is for the company to implement their side by writing software that follows the design. The last step is to put the resulting program on a server. Along with the server software, the company publishes documentation for the API. The documentation is one or more documents, typically web pages or PDFs that explain how to use the API. It includes information like what authentication scheme to use, what endpoints are available and how the data is formatted. It may also include example responses, code snippets, and an interactive console to play with the available endpoints. Documentation is important because it acts as a guide for building clients. It is where someone interested in using the API goes to learn how the API works. With documentation in hand, there are a number of ways you can begin to use an API as a client. So let's see how to implement as HTTP clients. An easy way to start using an API is with an HTTP client, a generic program that lets you quickly build HTTP requests to test with. You specify the URL, headers, and body, and the program sends it to the server properly formatted. These types of programs come in all sorts of flavors, including web apps, desktop apps, web browser extensions, and many more. The nice thing about generic HTTP clients is that you do not have to know how to program to use one. With the skills you have attained through this session and through the previous sessions, you have the ability to read a company's API documentation and figure out the request you need to make to get the data you want. This small learning curve makes generic clients great for exploitation and quick one-off tasks. There are a couple downsides to this approach. First, you usually cannot save your work. After you close the program, the requests you made are forgotten and you have to rebuild them the next time you need them. Another disadvantage is that you typically cannot do much with the data you get back, other than look at it. At best, you have the ability to save the data into a file, after which it's up to you to do something interesting with it. So we were talking about the downsides to this approach. So first, you cannot save your work. After you close the program, the requests you made are forgotten and you have to rebuild them the next time you need them. Another disadvantage is that you typically cannot do much with the data you get back other than look at it. At best, you have the ability to save the data into a file, after which it's up to you to do something interesting with it. So next is writing code. To really increase the power of an API, we will eventually need custom software. This is where programming comes in, being a discipline to itself. We won't attempt to cover everything about software development, but we can give some guidance for what writing an API client involves. The first requirement is to gain some familiarity with the programming language. There are a bunch out there, each with its advantages and disadvantages. For simplicity's sake, it is probably better that you stick to an interpreted language like Python, JavaScript, instead of a compiled language like C or C++. If you are not sure which language to choose, a great way to narrow down the selection can be to find an API you want to implement and see if the company provides a client library. Library is a code that the API owner publishes that already implements the client side of their API. Sometimes the library will be individually available for download, or it will be bundled in an SDK. Using a library saves you time because instead of reading the API documentation and forming raw requests, you can simply copy and paste few lines of code and already have a working client. So let's begin with chapter 1. Basics before the API. So before we actually start designing and developing our APIs, we need to understand some common terms. So we will start with World Wide Web, that is www. Introduction to www. So the web started in the data acquisition and control group at the European Organization for Nuclear Research in Geneva. It began with a computer programmer who had a clever idea for a new software project. Few months later, to facilitate the sharing of knowledge, Tim Berners-Lee started a non-profit software project that he called World Wide Web. After working diligently on his project for about a year, Berners-Lee had invented and implemented a uniform resource identifier, a hypertext transfer protocol, the hypertext markup language, the first web server, the first web browser, and the first HTML editor. So the URI, which is Uniform Resource Locator, Uniform Resource Identifier, is a syntax that assigns each web document a unique address. HTTP is a message-based language that computers use to communicate over the internet. HTML represents informative documents that contain links to related documents. Then he had also developed first web browser, web server, then the first web browser, which he named www. And it was later renamed to Nexus. From that moment, the web began to grow exponentially. Within few years, the number of web users increased to 40 million. At one point, the number was doubling every 2 months. The universe of documents that Berners-Lee had described was indeed expanding. The web was growing too large, too fast, and it was heading towards collapse. The web's traffic was outgrowing the capacity of the internet infrastructure. Additionally, the web's core protocols were not uniformly implemented, and they lacked support for caches and other stabilizing intermediaries. With such rapid expansion, it was unclear if the web would scale to meet the increasing demand. The web's traffic was outgrowing the capacity of the internet infrastructure. Additionally, the web's core protocols were not uniformly implemented, and they lacked support for caches and other stabilizing intermediaries. With such rapid expansion, it was unclear if the web would scale to meet the increasing demand. So how and what is the web architecture? In 1994, the people became concerned by the web's scalability problem. Upon analysis, they recognized that the web's scalability was governed by a set of key constraints. He and others set out to improve the web's implementation with a pragmatic approach. Uniformly satisfy all the constraints so that the web could continue to expand. The constraints were grouped into 6 categories and collectively referred to as the web's architectural style. They are client server, uniform interface, layered system, cache, stateless, code on demand. So we will discuss about this client-server architecture. The separation of concerns is the core theme of the web's client-server constraints. The web is a client-server based system in which clients and servers have distinct parts to play. This may be implemented and deployed independently using any language or technology, so long as they conform to the web's uniform interface. Then we have uniform interface. The interactions between the web's components mean the clients, servers, and network-based intermediaries depend on the uniformity of their interfaces. If any of the components stray from the established standards, then the web's communication system breaks down. Web components interoperate consistently within the uniform interface's 4 constraints, which are identified as identification of resources, manipulation of resources through representations, self-descriptive messages, hypermedia as the engine of application state. So in this, if we see identification of resources, each distinct web-based concept is known as a resource and may be addressed by a unique identifier like URI.